This is lecture 15. Today we'll be talking about molecular shapes and polarity of molecules. We're going to start with the shapes. We're going to learn something called VSEPR, or valence shell electron pair repulsion theory. So it's a really long name for saying that electrons like to get away from each other. So what we're going to do with VSEPR is learn how to go from a chemical formula to a Lewis structure to a three-dimensional molecular geometry here. And this actually isn't super complicated. The first step that we're going to do is just draw our Lewis structure like we've done here. And then once we have our Lewis structure, what we're going to do is determine the steric number of the different atoms in here. And you notice we'll only care about this for atoms that are bonded to more than one thing. So for hydrogen here, we're not going to worry about its geometry because it really doesn't have any geometry. It's just stuck onto this carbon. So we're really worrying about the geometry around this carbon here. So to count the steric number, what we're going to do is figure out how many electron groups there are around the atom. By electron groups, we mean lone pairs and bonding systems. So by bonding systems, basically we mean how many atoms are bonded to it. So for our steric number here, our Sn, we're going to count the number of atoms bonded to our central atom, the one we're worried about, plus the number of lone pairs on the central atom. Once we have that information, we're going to try and arrange the electron groups so that we minimize the repulsion between them. Another way of saying that is we're going to take all our bonds and all our lone pairs, and we're going to move them all as far away from one another as we can. And this will give us what's called our electron geometry. And then from our electron geometry, we can take that and we can ignore all the lone pairs on our electron geometry, and that'll give us what's called our molecular geometry. So in molecular geometry, we're just worried about where the atoms are located relative to each other. So I'm going to make this point really strong right here. Electron geometry does not equal molecular geometry. They are very closely related, but they are not the same thing, and you need to get those two separated out in your mind. So let's look closer now at the steric number and how it actually affects the geometry. So the basic idea is the steric number just tells you how many things there are around your atom, how many bonds, how many lone pairs. And then each of these electron groups is going to try and push as far away from the others as it can. So here in this example, I have balloons taped together. And of course, I didn't do this. These pictures got stolen from the internet somewhere. But as you can see, as we add more and more balloons, the geometry changes. Why? Because the balloons are trying to push away from each other. So there are 5 basic geometries, these described right here, with an Sn of 2. So that's our steric number. So steric number of 2, steric number of 3, 4, 5, and 6. And I've got some example molecules down here. So let's dive into these a bit. I'm going to rearrange these a little bit. So now we have it going from up to down. And you'll notice with each of these geometries, I have a name underneath it. So these geometries right here are the geometries that our electrons can be in. So our electron geometry is actually just limited to 5 different shapes. For a steric number of 2, you're going to get this linear geometry. It's named that because all the atoms are in a line. For a steric number of 3, you'll get a trigonal planar geometry. It's called trigonal planar because you have these 3 connected atoms that form a triangle. And it's called planar because they're all in the same plane. You can lay them out all on the same piece of paper. But when we go to our steric number of 4, we add another group on top. You'll notice now we are pushing those other 3 downward. So we're getting a different shape here. This is called a tetrahedral shape. Tetra means 4, and it's called 4 not actually because there's 4 points on it, but because if you wrapped this whole thing in foil, you'd get a shape with 4 different sides on it. Another way of thinking about this is a 4-sided die. So if you're a Dungeons and Dragons nerd, which I'm not right now, maybe someday in the future, but a four-sided die is going to have four corners, just like these four atoms would be here. For a steric number of 5, we're adding another atom back on the bottom. We're getting our trigonal planar thing coming back on here, but now we have a top poke and a bottom poke. I guess poke is a weird word for that. But we call this trigonal bipyramidal, because what we're saying is we have two triangular pyramids, one on top of the other, and so we say bipyramidal. These are trigonal bipyramidal because they're triangle pyramids. With a steric number of 6, we get this octahedral structure. Again, we have this octa, which means 8, even though there's only 6 things attached here. It's called octahedral because, again, if you wrap this thing in foil, you'd get 8 faces. So an 8-sided die is actually going to have 6 corners. Interestingly, a 6-sided die has 8 corners. Some weird info. But octahedral is a structure with a steric number of 6. Now I say that electron geometries have to be one of these 5 options. But molecular geometry is a little more complicated because in molecular geometry, if some of these atoms are replaced with lone pairs, for molecular geometry, we're not going to be caring about those lone pairs when we're describing our geometry. And so our molecular geometry can actually be any of these options on this table. So it can be these first 5. So the molecular geometry can match the electron geometry, or they can be very different, right? And FYI, there is a table like this in your book. You'll need to memorize all of these shapes. Fortunately, this is, I think, is one of the easiest tables to memorize because all the names are pretty meaningful, so they're not just random words. Plus, I don't know about you, but for me, talking about these shapes is just kind of fun. So this is, in my opinion, one of the funner lectures to teach. So let's go through each of these rows systematically now. We'll start with our steric number of 2. So here we have a central atom with either 2 atoms attached or with an atom and a lone pair. In this case, you're going to have a bond angle, so the distance between these 2 bonds is going to have an angle of 180 degrees, and that's pretty much all there is for linear stuff. There's not much complications here. I will throw in too that if a molecule just has 2 atoms, so let's say we just have 1 carbon and 1 oxygen, we're still going to call that a linear molecule, because if you have 2 atoms, you can draw a line between them. Though, if there's only 2 atoms, we don't talk about a bond angle because the bond angle is a measure of the angle between 2 bonds. If you have a molecule with just 2 atoms, there's no angle to measure there. All right, let's go on now to get a little more complicated. The trigonal planar geometry that we get with a steric number of 3. In this case, these atoms or electron groups are all going to push as far away apart, and that's going to result in them all having a 120-degree angle between them. So they'll have a bond angle of 120. So if you have 3 atoms attached, your molecular geometry will still be this trigonal planar. But if you replace one of those atoms with a lone pair, the electron geometry will still be trigonal planar, but now the molecular geometry we're going to say is bent. So when we're talking about the atoms relative to each other, they have this bent structure. Okay, so make sure you can tell what this molecule's electric geometry and molecular geometry are. All right, let's go now to a steric number of 4. In this structure, we get the tetrahedral, and this is actually probably the most common shape you'll encounter. So carbon generally adopts this shape unless it has a double or triple bond in it. So this is a very common shape. In this case, the bond angle, the angle that all the bonds are going to have to move away from each other, is 109.5. So remember that 109.5 is the bond angle here. Now this one is fun because if we start taking atoms off and replacing them with lone pairs, we get one shape that's trigonal pyramidal. So if we take one atom off and replace it with a lone pair, then we still just have three atoms attached, but they're all pointing down because you got the lone pair on top pushing them down. And so this is a trigonal pyramidal structure. It's not the trigonal bipyramidal because it only has one pyramid in here, but it is still a trigonal pyramid. And then if we take another atom off and put another lone pair on, we actually get another bent structure. So you can get the bent structure with more than one electron geometry, or in other words, more than one steric number. So here, our electron geometry is still tetrahedral, but our molecular geometry would be bent. All right, for a steric number of 5, this one is actually the most complicated. It's the most complicated because to get all this stuff arranged, you actually have to have two bond angles. So we have these atoms here in the middle that we call the equatorial atoms, and then the two atoms pointing up and down we call the axial atoms, and the bond angles between all of these are different. So the bond angle between the equatorial and axial atoms here, as I'm showing in this diagram, is actually 90 degrees, but the bond angle between two equatorial atoms is now 120 degrees. And the bond angle between the two axial atoms is 180 degrees. So you really get three different bond angles in here. We mostly just talk about this 90 degree and 120 degree angle. But so this steric arrangement makes the trigonal bipyramidal geometry the most complicated. It also makes it complicated because then once we replace one of these atoms with a lone pair, we have to decide, well, should we replace the atom or an equatorial atom, or should we replace an axial atom? Now, the answer here might surprise you a little. So lone pairs actually need more space than bonded atoms. So if we have a lone pair, it's going to need to be as far away from everything else as possible. So it actually gets more space here if it's an equatorial electron or an equatorial lone pair. And so your lone pair is going to always be substituted on your equator. And that's going to have some significant ramifications for the structures of these guys. So now if we look at the structures, if we start replacing lone pairs, if we replace one lone pair, we get this geometry where we still have our axial atoms, and then we have two equatorial atoms. And this structure, this geometry, we actually call sawhorse. That's a phrase that's borrowed from construction. So in construction, if you need to saw something in half, so let's say you have a long beam of wood, and you need to saw it in half, you'll put it on two of these sawhorses, and it'll balance in between. Then you can saw it real easy. You're not sawing on the ground, because if you try and saw while you're in concrete, it makes it a little hard to get all the way through and so forth. So one electron gone, you get this sawhorse structure. With two electrons gone, you get this T shape, which is just named because it's in a T shape. And then if you lose three atoms and get three lone pairs, you actually get back to our linear structure. So you can get the linear structure with more than one electron geometry as well. So remembering that you replace equatorial atoms in the trigonal bipyramidal structure is really going to be key to getting these types of structures right. Lastly, we'll talk about the octahedral structure we get with a steric number of 6. So with a steric number of 6, you get this geometry, and you'll notice again, octa means 8, but this has 1, 2, 3, 4, 5, 6 atoms attached. So we call it octahedral again because if you wrapped this whole thing in a tight sheet of foil, then that foil would have 8 faces on it. So it'd be similar to an 8-sided die. The bond angles here are all 90 degrees. So the bond angles between each individual atom Can also talk about the bond angle between atoms on different sides, which would be 180 degrees, but we really don't talk about that much. Now, when we start taking electrons off of here, we do have to be somewhat systematic, at least in, when we're taking atoms off, we have to be somewhat systematic. So the first atom we replace with a lone pair can go anywhere, but the second always has to be on the opposite side of the first. So if you're going to have two lone pairs in an octahedral electron geometry, the lone pairs have to be opposite one another. And then two, after you've got three lone pairs and you move to a fourth, that fourth has to be opposite of the third. Right, so we're not getting these all kind of bunched up. We're trying to spread out the lone pairs. So if we replace one atom with a lone pair, we get this structure, which is actually a square pyramidal. So here we think of our pyramid having a base with four corners, and we got a point on the top. So this would be a four-sided pyramid, like real pyramids in Egypt. If we take two atoms off, then we've got a lone pair on either side of this molecule. We actually call this a square planar geometry. If we take three atoms off, we've got three lone pairs. Now again, we actually get the T-shape again. So we saw this with our steric number of 5. So we can get the T-shaped molecular geometry with two different electron geometries. You'll notice a lot of these have the same name, which makes memorizing the names a little easier too. And then if we get down to 4 atoms removed, then now we have a linear structure again. So we can get the linear structure from a number of these geometries as well. All right, so those are your geometries. Remember, you need to memorize all the possible molecular geometries. Really, there are some principles there, so it's not pure memorization. It's understanding where you take the electrons or the atoms from and where you put the lone pairs. And then you really just name it based on what it looks like. So in memorizing these shapes, I've personally never actually looked at a table to memorize it. For me, it was intuitive. If it's not intuitive for you, try and make it intuitive by learning those rules and also memorize the table. But learning the rules is really going to be more helpful in the long run. So with that, let me give you an iCLICKER quiz and tell me what the molecular geometry is of PCl3. So for this, you're going to have to draw the Lewis structure and figure out the steric number and then the geometry. Go ahead and pause the video and do that. All right, what you should have gotten is something that looks like this. So phosphorus should have a lone pair above it, and it should be forming 3 bonds, one with each of these chlorine atoms. So if we look at this and calculate our steric number, you should get a steric number of 4 because you have 1, 2, 3 atoms attached and you have 1 lone pair. So that adds up to 4. So we get an electron geometry of tetrahedral. But because we have this lone pair up here, that's not going to be our molecular geometry. Our molecular geometry is going to be trigonal pyramidal. So that will be our correct answer. So here will be another great place for me to emphasize the point that electron geometry is not molecular geometry. So this is one of the most common stumbling points with this topic for students, is confusing electron geometry and molecular geometry. So make sure you get those straight right now. All right, now let's also get into bond angles. So I gave you a lot of bond angles, but the bond angles for the different structures are actually for the ideal structure, which we almost never have. So for example, here with ozone, this is the molecule we talked about back when we were talking about resonance. We have this structure for O3 where we have this central oxygen atom. It's bound to 1, 2 atoms with a lone pair on top, so it has a steric number of 3. And it has a steric number of 3 regardless of which resonance structure you're looking at. So all of your resonance structures should have the same steric number for your central atom. But the bond angle here, for a steric number of 3, that would give us a trigonal planar geometry, or for electron geometry, and we got our bent molecular geometry. But the bond angle here is not 120 degrees like we would expect from a trigonal planar geometry. The reason for that is actually this lone pair up here. So like I said, when we're talking about our steric number 5 molecule, where we have this trigonal bipyramidal structure, you got to replace atoms at the equatorial sites first with lone pairs. The reason for that is because lone pairs actually just take up more space, and they'll actually push other stuff out of the way. So the reason the bond angle here between these two oxygens is less than ideal is because the lone pair is going to take up more room than bonded atoms. So the idea here for estimating bond angles, you won't actually be calculating bond angles, you'll really just be making statements about bond angles. But the idea is that lone pairs repel a lot. So they really like to push everything else away from them. Another way of saying that is lone pairs take up the most space. Next comes double and triple bonds. These like to repel each other a little bit. So they will take up more space than single bonds, but less than a lone pair. So double and triple bonds, they take up a medium amount of space. And as you can imagine, a triple bond will take up a little more room than a double bond. But usually if you have a triple bond, then you're just going to have a single bond on the other side. So most of the time, we're really just worried about double bonds with this. And if what I just said about triple bonds doesn't make sense, that's fine. You can survive without understanding that statement. And then last on this hierarchy is the single bonds. These repel the least, so they take up the least amount of space. So if you just have 4 single bonds, no electron pairs, then you can basically think of it as just everything getting as far away from each other as possible. So let's take this idea now and let's walk through a molecule and figure out the geometry around several of these atoms. So for each of these, we're going to figure out the molecular geometry and make a statement about the bond angle. So you'll notice I'm not saying we're going to actually give the actual bond angle, we're just going to make a statement about it. So if you want to try this on your own, go ahead and pause the video now, try and figure out the geometry around each of these. All right, so this first bond angle is between this hydrogen and carbon. So we've got our central carbon here. First, let's figure out our steric number. It's bonded to 3 things. It's got no lone pairs, so it's got a steric number of 3. So this is going to be a trigonal planar geometry. Now, trigonal planar geometries generally have a bond angle of 120. However, we have this double bond down here, which is going to squish this bond angle to smaller. It's going to basically push this hydrogen towards this carbon and this carbon slightly towards that hydrogen. So we're going to have a trigonal planar geometry with a bond angle of slightly less than 120 degrees. For number 2 here, let's figure out our carbon is our central atom and it's bonded to 1, 2, 3, 4. So we can figure out a steric number of 4. There's no lone pairs. So for a steric number of 4, we're dealing with a tetrahedral electron geometry. And since there's no lone pairs, our molecular geometry will be the same as our electron geometry. So it'll be tetrahedral. And in a tetrahedral geometry, we'll have bond angles of 109.5. All right, number 3 here, our central atom is this carbon, and we're looking at the bond angle between the 2 oxygens. So in this case, our carbon is bonded to 1, 2, 3 atoms, no lone pairs. So it's got a steric number of 3. So that again will be trigonal planar, just like up here with bond number 1. The difference here though is that we're looking at the angle now between the double bond and a single bond. That double bond is going to take up some extra space. So the bond angle here is actually going to be greater than 120 degrees. So you'll notice that the bond angle here is actually not drawn correctly. We didn't draw the right bond angle. Up here in angle number 1, the bond angles around this carbon are all drawn correctly. But as you'll find out as you draw these structures, it's not always practical or even possible to draw the correct bond angles. right? So for bond angle number 2, the central carbon, there's no way to draw a bond angle of 109.5 between all of these. For number 3, we could actually draw a bond angle or correct bond angles here, but oftentimes we won't, so that we can keep this portion of the molecule off of this portion of the molecule, and so we just have space to write everything, right? Because these are all really branching out in 3 dimensions, and we have to draw it in only 2 dimensions. And so there's some practical considerations there. All right, let's talk about angle number 4. We've got oxygen as our central atom. We've got carbon and hydrogen that we're trying to compare. If we look at the drawing here, you might assume the bond angle is 180 degrees, but then you would be terribly, terribly wrong. So the first thing we need to do is figure out our steric number of this oxygen. It's bonded to 2 atoms, and it's got 2 lone pairs, so it'll have a bond angle of, or sorry, a steric number of 4. So a steric number of 4 gives us a tetrahedral electron geometry, and we've got 2 lone pairs in here, so our molecular geometry will not be the same as our electron geometry. Our molecular geometry is actually going to be a bent structure, and in our tetrahedral electron or electric geometry, we'd expect a bond angle of 109.5, but because we have a couple of lone pairs here, we're actually going to get a bond angle of less than 109.5. So we have a bent structure and a slightly smaller bond angle than we'd expect. Let's finish off this discussion with bond angle number 5 here. So our central atom is nitrogen, and we're looking at the angle between 2 hydrogens. Nitrogen has a steric number of 1, 2, 3, 4, so it's bonded to 3 things, and it has 1 lone pair. So that's going to give us a tetrahedral electron geometry, but we have 1 lone pair. So now we're actually talking about a tetrahedral where we take off the top and we're just left with a trigonal pyramidal geometry on the bottom. And again, our bond angle here is going to be less than 109.5 because we have an electron geometry that's tetrahedral, and we have that 1 lone pair there that's going to scrunch the other bond angles down. Okay, with all that, let me give you a practice to do, or another practice to do all on your own. Based on what you know about electron-electron repulsion, which of the following is correct about the HOH bond angle in H2O or water? Go ahead and pause the video here, try and figure this one out. All right, the first thing you should do in these problems is draw the Lewis structure. Now, if you draw the Lewis structure for this, you should get an oxygen singly bonded to 2 hydrogens, and then you should get 2 lone pairs on that oxygen as well. So this water molecule has an electron geometry that's tetrahedral, but it has a molecular geometry that's bent. So in a tetrahedral, you have a bond angle of 109.5, but when you add some lone pairs in that, you're going to scrunch the bonds, the angle between bonds, down a bit. So it's going to be less. And we can actually compare this molecule that has 2 lone pairs to one that has a single lone pair, like NH3. So NH3 also has a tetrahedral electron geometry, but it actually has a trigonal pyramidal molecular geometry. And you'll notice the bond angle here is 107, which is about halfway between 104.5 and 109.5. So if you have no lone pairs, you're going to have a geometry of about 109 or with bond angles of about 109.5. If you replace one atom with an electron pair, you get a bond angle of 107. If you replace 2 atoms with lone pairs, then you get a bond angle of 104.5. So more lone pairs, the smaller the bond angle. So that's it for geometry. We'll move on to polarity on the next slide. But like I said, make sure you get all those geometries memorized and understand the difference between electron geometry and molecular geometry, and then also be able to predict how bond angles are going to be affected by different electron groups. All right, now let's move on to polarity. So we've already talked about polarity a little bit in the past, and none of our ideas are really going to change. We're still dealing with a molecule where we have a uneven distribution of electrons. So the electrons are spending a little more time in one region than they should. But now, if we know the three-dimensional geometry, we can get a little more complicated with our understanding here. So it's still going to be, if I have this water molecule here, we're going to have these dipole bonds or polar covalent bonds in here. We're going to have a partial positive on our hydrogens and a partial negative on our oxygen, right? This stuff is all stuff we've said before. And this is just because oxygen is more electronegative than hydrogen. So now the individual bond dipoles are going to look like this, but the overall molecular dipole is going to be an average of those other two dipoles. So the molecular dipole will point from between the hydrogens through the oxygen here. So if you're trying to figure out the polarity of a molecule, you're going to have to now include this geometry idea. So what you're going to need to do first is draw the Lewis structure. And then once you have the Lewis structure, figure out your geometry, and then look for your net dipole, right? You're still looking for polar bonds, and then you're going to try and add those up to see if they cancel each other out or if they support each other. All right, so in here in this table, I have just a bunch of polar molecules, and we'll talk about the strengths of their dipoles now. So with HF, this is about as polar of a bond as you get. Fluorine is the most electronegative atom on the periodic table. When you bind it to hydrogen, you get this dipole running from the hydrogen through the fluorine. And this has a strength of 1.91 debye. Now, if we get a bent structure like this for water, this is what we're just looking at, right? We have these dipoles moving along the bonds here between oxygen and hydrogen, but how the molecule is going to behave as a whole is going to have to consider all of its internal dipoles, right? So it's going to have to take an average of all of those, or actually it's going to take the sum of them all. And if we sum these two vectors together, we'll get a dipole pointing up through there, right? The same is true for a trigonal pyramidal structure like this. Here we have NH3. We have these three nitrogen-hydrogen bonds. So these are all polar, but you'll notice in NH3 you have three polar bonds, whereas in water you only have two, but the dipole moment in NH3 is actually weaker than it is in water. Why is that? Well, because when you're adding these three in NH3, they're all facing basically different ways. They all have some amount that's pointing up, but other than that, the part that's pointing into the nitrogen is now all canceling each other out. And so you still get an overall dipole pointing from between all three hydrogens up through the electronegative nitrogen, but it's a little weaker now. And if we have something like this, where we have CH-Cl3, here what we're dealing with is a carbon attached to three chlorines, right? And we also have some polarity along this CH bond. The electronegativity between carbon and hydrogen is small, so we'd only say it, or we'd actually call that a nonpolar bond, but that nonpolar bond in the presence of a bunch of other polar bonds can add just a little bit to the overall dipole of the molecule. So here you just kind of have to add up everything together. You get an overall dipole facing from the hydrogen down through the electronegative chlorines, so through the middle of them. And now this last one, we have a molecule. It's got four polar bonds. They're all kind of competing with each other, right? We have this tetrahedral structure where they're all facing away from each other. And if this was carbon bonded to four chlorines, this molecule would actually overall not be polar because all the dipole moments would cancel each other out. However, in this case, fluorine is a little more electronegative than these chlorines, and so its dipole moment is going to be slightly stronger. So we'll still get a dipole facing up, and it'll have it'll have a relatively small strength because it's fighting these other dipoles. So those are the kind of thoughts you need to have while you're working through these problems. I'll finish this off with just one last iCLICKER quiz, or I guess a quiz with 3 questions. So we'll go through these one by one, and I want you to say, we'll start with NH3. I want you to tell me if it's A, polar, or B, non-polar. And then we'll do CH4, and then we'll finish off with COH2 over here. All right, so go ahead and just pause the video now and try and answer all 3 of these. All right, for NH3, this has a steric number of 4, so it has an electron geometry of tetrahedral, but it's got a lone pair, so it's going to have a molecular geometry of trigonal pyramidal, and nitrogen is an electronegative atom, so all these NH bonds are going to be polar covalent bonds, and they're going to add up to give us a polar molecule. All right, CH4. This has a steric number of 1, 2, 3, 4. Anytime you have something like this where your steric number is equal to the number of bonds you have, and your central atom is bonded to the same element 4 times, another way of saying that is if your central atom has no lone pairs and it's just bonded to the same 4 things, it's going to be nonpolar. Because even if each of these bonds was polar, which in this case they're not, but even if they were, they would all cancel each other out. So this is a nonpolar molecule. All right, now we have COH2. Here we have a steric number of 3 for our central carbon, and it is going to be bonded to 1 electronegative atom and 2 not so electronegative atoms. And so this is going to have a dipole running from actually just down in between the hydrogens on up through the oxygen there. So this will be a polar molecule. All right, let me know if you have any questions about any of that. I'll be happy to help you out.